2 p.m. And yeah, the meeting is being recorded, just so you know. So we're delighted to welcome today Associate Professor of Biomedical AI at the University of Edinburgh, Ava Khamesh, and she's going to talk about the causal roadmap for generation of reliable real-world evidence with application to genomics and biomarker discovery. She's going to talk for about 50 minutes, and then we'll have some time for Q&A at the end. Yeah, Professor Khamesh.
Thank you very much. And thank you for the opportunity to present here today. So I'm just going to jump straight into this. Just first making sure this thing goes away. Sorry, I'm not sure. Can you see my slides?
Yes.
Yes. Okay, perfect. So just starting from the definition of real-world data as defined by the National Institute for Health and Care Excellence, NICE. Real-world data is data relating to patient health or experience or care delivery collected outside the context of highly controlled clinical trials. So examples of this type of data includes data from primary care. A famous one in England is CPRD. So these are anonymized patient data from GP practices and potentially linked to hospital records of millions of patients. Here in Scotland, we have, for example, DataLog, which is NHS Lothian and South East Scotland data of health and social care routinely collected from individuals here. Now, these real-world data can also be prospective. So UK Biobank is a good example of an observational cohort of 500,000 individuals with de-identified genetic, lifestyle, and health information, which also collects, as part of it, some primary data as well. Other famous examples are the All of Us dataset in the US, and more recently, our Future Health, again in the UK, of 2.5 million individuals plus. Now, depending on the source of real-world data, primary care, prospective, cohorts, and so on, there are different strengths and weaknesses in terms of numbers of individuals, numbers of measured features per individuals, and missingness. And as a result of this, all these types of observational data, i.e. data where interventions exposures are not determined by study protocol, but by patients and healthcare professionals, need generally applicable methodologies that makes the situation more challenging than a well-designed, well-controlled type of clinical trial. Now, real-world evidence is defined as evidence generated from the analysis of real-world data, and this could be in situations where randomized controlled trials are not possible or not applicable due to ethical or feasibility considerations, costs, small number of eligible patients. It may be the case that certain comparators are not applicable to standard of care in the NHS. There may be limited follow-up, differences in the population between the trial and the general population, and also importantly, differences in clinical support during a well-designed situation, whereas real-world data. MHRA in the UK, the regulatory body, considers examples of the following as real-world data and real-world evidence. So even if we have clinical trial where real-world data is used as an external control arm, or pragmatic trials embedded in routine clinical practice, essentially involving electronic health records. And if you go on the MHRA website, there's a statement that it is not necessarily the case that real-world data or evidence submitted from this type of data is considered any lesser than a randomized controlled trial, as long as things are well designed and the methodologies are appropriate for this type of data. Now, increasingly, regulatory bodies, including NICE and MHRA, FDA in the US, and EMA, the European Medical Agency, are embedding real-world evidence generated from real-world data in their scientific evaluations of medicine to inform health economic models and in general policy and guidance. And this is because we've had a massive increase in both breadth and quality of real-world data, as well as, importantly, methodological advances in causal estimation in recent years to support this type of healthcare policy and regulatory decision-making. Now, despite this, in contrast to traditional clinical trials, some people are concerned about potentially biased effect estimates using real-world data. and as a result are cautious and critical in interpreting real-world evidence findings. Now, there may be multiple sources of bias or the risk of overgeneralization. These are the three main ones. So one is sampling bias, and this is related to the fact that the population on which we're doing the estimation are in fact different from the real target population of interest. This sampling bias, you could also have it in RCTs. And in fact, that's one of the main reasons people want to, in addition to RCTs, have real-world evidence, data, evidence and data as well. Then there is the matter of causal bias, which is more challenging when dealing with real-world data than RCTs. And this, for example, is related to unmeasured confounding, leading to lack of randomization of the treatment. Another example of this is collider bias that leads to non-causal associations between a treatment and outcome variable, and that there are very many more examples of how this can occur. And finally, there is also statistical bias, which quantifies the extent to which the average estimate across many samples deviate from the true unknown value of the estimate. And if I were to pictorially represent this, if I have a model or an estimator that is biased relative to what it is trying to measure, so it's off in terms of the data generating distribution, at small sample sizes, this may not be so bad because the error bars are large because of the large variance. I somehow get lucky, and with an error bar, I cover the ground truth. However, as the sample size grows, an estimator that is biased gets progressively worse. And so I end up estimating something wrong very confidently. So the error bar shrinks and I move away from the ground truth. Now, in contrast, if an estimator is unbiased, the way it's supposed to behave is as the sample size grows and the variance shrinks, I get closer and closer to the ground truth in a more precise manner. Now, in general, the problem with this is we do not know where the ground truth is, which is why we're doing the study in the first place. And so what I'm going to present today is that we need mathematical guarantees that our estimator is behaving or is going to behaving like the situation on the right-hand side and not the disaster on the left-hand side. And again, this is important because there is a lot of emphasis on we need more data, we need larger sample sizes, but with that larger sample size, there comes the responsibility of ensuring we don't end up getting massively confidently wrong answers as compared to unbiased estimation. Now, a recent review of real-world evidence studies in 2022 reported that nearly all studies that they reviewed, 95% of them, had at least one avoidable methodological issue that incurs bias. This review was from 75 studies, 10 of them were case control, and 65 of them were cohort studies on areas of common disease, such as cardiovascular, diabetes, and osteoporosis, based on insurance claims that were made in the US. So I'm just wanting to let that sink in. This is not good. We should not be in this situation, and we should try to sort of improve what we're trying to do. So one proposal that it's really taking a lot of attention in recent years is this approach of the Causal Roadmap by Van der Laan, Peterson et al., developed in the US. And the idea is to, regardless of the problem, try to formulate and break it down into steps and follow these 6 objectives. The first part of this starts with very clearly defining the causal question of interest, the causal model in the sense of what kind of variables are involved, what is the relationship between those variables, and importantly, related to the causal question, the causal estimate. So what is the quantity we're actually trying to, down the line, estimate? And so related to the question, just to give a very simple example, maybe I'm interested to know what is the effect of an old treatment versus a new drug that has come on the market on improvement of some clinical outcomes, such as a cardiovascular event. And if I'm using real-world data from, say, the NHS, there are a bunch of confounding variables, so those are features of the patients based on which a doctor assigns the usual treatment or the new treatment. And those features themselves may affect the actual clinical outcome in their own right. And so I need to be careful that when I'm looking at a certain data frame to start making estimation, when I say something is a confounder, Is that baseline? Is it not baseline? Does it change over time? Does that affect treatment or not? So all these relationships need to be well defined at the beginning. The question is defined at the beginning, and importantly, the inclusion and exclusion criteria needs to be defined at the beginning. The emphasis of doing this before we actually worry about do we have causal identifiability, how we estimate and so on, is so important because it matters how we define the population in the first place, relevant for the question of interest. And when we do causal inference, we have to link to, okay, I made a statement about this population. It doesn't generalize to other kinds of populations if I start including, failed people or pregnant people or whatever, because that's not how the population was defined in the first place. Now, dealing with this is well known in this literature as target trial emulation is a way of doing it. It's from Hernan et al. And the causal roadmap that I'm talking about today is fully compatible with target trial emulation, whose emphasis is on this first bit about the data, inclusion, exclusion, the research question, and a priori knowledge about the data generating distribution. The rest of this that is specific to the causal roadmap that was emphasized by van der Laan et al. Is related to model independent definition of a causal quantity. So this is a situation where we, without reference to a particular model, whether it's linear or deep learning or whatever, what we're trying to do is to say, okay, the verbal question has to be formulated in terms of a mathematical ideal quantity that we want to estimate. So in this particular example, I want to know the cardiovascular outcome under the new drug versus the cardiovascular outcome under not the new drug, i.e. the usual treatment that's already on the market. And so this is one way of defining this quantity. Perhaps for a different type of question, I'm not interested in an additive scale, I'm interested in a multiplicative scale. Perhaps I want to take the ratio of these two quantities. So this thing differs per question. What I'm writing here is an example of this type of scenario, and people later call this average treatment effect. But again, this can be as complex as you want, maybe time varying, there may be unmeasured confounders, whatever. So I'm not talking about that. I'm just saying there is a question and there's a corresponding mathematical idealized statement that we can write down in a model independent way. The step after this is the causal identification step, which is to figure out if this idealized mathematical quantity can be written in terms of something that can be estimated from data. So I might in my head say, I want to know what is my clinical outcome if I receive the new drug versus when I don't receive the new drug. But I cannot turn back time for myself and figure out what happens under one intervention or another intervention. So what we want is some sort of a population average statement where we can say, under certain assumptions that are mild, I'm able to make the statement that this idealized quantity can be written in terms of something estimable from data. And what we're trying to do here, and I'll try to go through this equation here, is to shut the causal gap. But this doesn't mean the game is over. Then the major step comes in after that, and that is the actual statistical estimation of this quantity. So we've done all this hard work of defining the problem, defining the population, defining the idealized estimand. We've gone through causal identification, so we do not want to be in a situation where we make mistakes by choosing a biased statistical model. So what we want to do is we want to benefit from techniques that have the mathematical guarantees of shutting the estimation gap here. And then at the end, we can worry about sort of certain sensitivity analyses and causal interpretations of the results and so on. Okay, so for today, I'm not going to go through anything related to target trial emulation. Suppose that we have defined everything appropriately. My three main messages today is to keep causal identifiability and estimation separate in generating high quality real world evidence. The second is to agree with the subject expert on a model independent definition of the question of interest before the analysis begins. And the final point is on statistical machine learning methodologies, such as the example today is the same parametric efficient estimation or targeted learning that have proven mathematical properties to reduce or annihilate model misspecification bias and also to maximize power. And I'll showcase this with some simulations. Okay, So just to have some problem at the back of my mind, our minds as we go through, again, as I mentioned, we're comparing two treatments. Suppose I'm looking at some major adverse cardiovascular event as an outcome, and I want to know if GLP-1s are better or worse than SGLT2I. So these are two different newer kind of drugs that are on the market, and perhaps we're in a situation where the regulatory body wants to know is it worth to take one or the other, or is the subpopulation that benefits from one or the other? So a type of question or an interventional effect estimation that we want to ask in the sort of very classical way is this 8, which treatment leads to an improved outcome? Of course, typically we want to take this further. We want to say, well, given a certain feature of the patients or given their blood sugar levels, then which treatment is better, 1 or 2? Now, you can make this question very refined and ask about optimal treatment rules. So we want to say for patients with all these sets of features, and this can become a lot more high dimensional, so BMI, blood sugar, history of stroke, and so on, which treatment offers the best outcome? And I want to just pause here and emphasize something about these optimal treatment rules or very fine-grained conditional average treatment effect. For people who come from the machine learning side rather than the sort of the mathematical statistics side, this very much looks like a prediction problem that we now want to make causal. So there's a bunch of features and we want to know based on those features causally what treatment intervention is the appropriate one. And what I want to emphasize is that a lot of these problems can similarly be formulated as an estimation problem. And all these double robust methods that I'm defining here are readily available as a solution to this kind of problems. It's just to be careful in brackets not to sort of reinvent the wheel on some of these problems. Another example of this is mediation analysis. And perhaps we want to make the question more refined and say, to what degree is the effect of the treatment on this clinical outcome mediated through weight loss? Why would I care about this? Because, for example, if the effect of the drug on outcome is entirely through weight loss rather than any other direct effect, perhaps there are other strategies than giving the drug to target weight loss. And then I have to worry about later on, from a regulatory perspective or from a health policy perspective, which is the best. And that includes sort of economic benefit of these solutions as well. Okay, so just for the sake of argument and to keep things simple, I'm just going to focus on the sort of the classical average treatment effect as we go through the estimation together. But again, as I said, this can apply to something as complex as optimal treatment rules or mediation and so on and so forth. Okay, so mathematically, the true causal quantity, the idealized one that we're interested in estimating, is the outcome under treatment versus outcome under the alternative treatment for every person. We would love to either have a clone of them or go back in time, do the other intervention and take the difference. Now, usually this is not possible, so we have to try this out as a more of a population or a subpopulation estimate. So our goal is to obtain an estimate that I'm going to call psi hat of the parameter psi c, where the c stands for causal. So instead of having an idealized causal quantity, I need to be able to estimate this statistically from real-world data. And as we emphasized, these two quantities, y1 counterfactual and y0, cannot be measured together at the same time for every individual. Now, if I have the right relationship between the variables in the DAG under certain causal assumptions that I'm not going to go through here, it turns out that this idealized quantity can be written in terms of something that is estimable from the data. So even though I don't have this counterfactual y1 or y0 for every person measured, it turns out that I can write this mathematical idealized quantity in terms of something that doesn't depend on any counterfactual variables. Y is measured, W is the features that are measured, and the treatment status is also measured. Now, this equality fails if I have, for example, missing confounders. So I have to change strategy. Maybe I can figure out a way of rewriting this in such a way that the equality will be true on the missing confounders, but this particular one that I'm writing here will not hold if there are missing confounders. There are other situations. As an example, a feature of the patient may completely determine what kind of treatment they get. So, for example, if they have diabetic kidney disease, only one kind of treatment will be assigned and not the other. And again, this goes back to where we emphasize we have to define the population well, because in this situation, we'll have what is known as full positivity violation. And there's actually no point doing causal inference because they would, for that drug, because they are taking one drug anyway and never the other one. So we have to, again, be careful on how the population is defined and how it matches with the question of interest concretely. Now, if we decide in discussion with the subject expert that the causal assumptions are met, then we have to commit to a statistical estimand or a quantity, a parameter of interest. And in this particular example, it turns out to have this form. So as before, our goal is to estimate, to obtain an estimate psi hat of psi c via what I'm going to call a psi s, and I'll try to explain what this means. So to get the true causal quantity of interest, we want to minimize both the causal gap and the statistical gap. So it's not just enough to shut one of them, we have to shut both. So we're trying to get an estimate of psi c, and we want this ideally to be zero, this difference to be zero, so that we're really landing on top of the true causal estimate. Now, what we end up doing in practice is, fitting, and this fitting procedure, that this model may be off from the true statistical quantity. And if it is, this gap leads to what is called estimation bias. And then separately, there could be a difference between the ideal statistical quantity you want to estimate and the causal quantity you want to estimate, and this leads to a causal gap. And these are two separate problems. The one on the right is related to making mistakes with causal identifiability. The one to the left is about making mistake in the statistical or machine learning estimation procedure. Examples of the one on the right is the missing confounder I mentioned. An example of the one on the left, the statistical gap, is model misspecification. So the model that I've chosen, my favorite deep learning model, or my favorite linear model with interactions, polynomial model, XGBoost, whatever it is, that model is not reflective of the data generating distribution or the joint probabilities between the variables. And as a result, I'm misspecified. And as the sample size grows, I'll end up getting more and more biased estimates. So this is the kind of thing we're trying to avoid here. So emphasis, these are two separate issues, and we want to keep causal identifiability and statistical estimation separate. And that ticks off the first message. So now let's start with the model independent definition next. Okay. So in the case of an average treatment effect, again, just to keep everything simple, we think about the data generating distribution. And so we have our outcome, we have our treatment, and we had our patient features as confounders. And we know that there is some underlying true data generating distribution, and I'm going to call this P naught. So this probability of the truth that is unknowable to me is somewhere out there. And what we're interested in is, if we have identifiability, is to estimate the following quantity. So we're looking at stratifying individual based on their confounders and asking what is the outcome on the treatment versus the alternative treatment. Now, it's very important that we come up with a model independent definition of the quantity of interest. And the reason is as follows, is that if I show up and say, I want to fit this model using this parametric form at the top, and I ask you, what do you think is the treatment effect? And someone might look at this and say, well, I think it's beta because that's the coefficient behind T. And then someone else comes up with a different model, and this time there's an interaction between one of the features and the treatment. And perhaps this person says, well, I have beta, but then I also have T here, so I'm gamma and W1, so what do I do with that? Okay, so it turns out that in this case, it's the effect will be beta plus gamma and an expected value, an average of W1. And then I show you this, and I'm like, well, what's the average treatment effect in this case? Now, it turns out that it's you can derive that analytically, and it's a sort of few lines, and it depends on the joint probability distribution between T and W. It's a function of some of these coefficients in a non-trivial way. So Without a statistical model, the target is implicit and model dependent. So if I fit the data one way and someone fits the data the other way, it's not just that our fits are different, the thing we're actually measuring is different. So we're comparing apples and oranges. And that's not good because we should agree on, in a model independent way, what is the target quantity of interest. So if we look at the quantity here on the top, we have not referred to any coefficients. We're just saying there is some underlying probability distribution, and what we want is the expected value under this type of stratification on the treatment and no treatment. So this is entirely model independent, is written in terms of expectations or probabilities, it's not referring to any kind of coefficient. And I'm going to come back to this because this is a huge issue that should be absolutely avoided. So going back to the NICE guidelines on real-world evidence, the current suggestion is two routes for estimating this type of quantity. The first one that is suggested, I quote, if there are many potential confounders, more complex methods such as multivariate regression or propensity score methods are preferred. So we have this quantity, and sort of one of the examples of a multivariate regression is to take the outcome, disease outcome, and just fit that with some model as a function of the treatment and the features. And again, I'm writing this in this way. It could be a linear model, it could be deep learning, it could be whatever on the right-hand side. Now, if I happen to do ordinary least squares, maybe I'll do such a fit. And then this is where the guideline is implicit. So you could have someone that goes and says, I'm going to just call beta, and I'm going to do inference on beta, get an error bar, compute p-values, and say, this is the effect size. Now, what I just showed you on the previous slide is that if someone were to do something different, it's not that they are estimating beta differently, it is that they are estimating something different. So the effect size is not even comparable in this situation. So at the very least, even if we're fitting parametrically and so on, what we should do is use what is called a substitution estimator. That is to say, we start with a model independent definition. Let's fit y as a function of w and t however we want, but let's not read off a coefficient and instead plug that fit back into this equation and extract from that what the average treatment effect is. So I have y as a function of w and t, let's call that q, w and t. I plug this quantity back into the model independent definition and I evaluate it at t equals 1, I evaluate it at t equals 0, and then I'm taking an average as suggested over all the confounders. So in this situation, at least if someone comes with a different fit q, we're all doing the same thing in spirit. So the fit is different, the inference will be different, obviously, but at least we are estimating the same quantity, which is this quantity at the top. So this does appear in FDA guidelines that this is off limits. So it's a sin to reading to read off coefficients in models. So we're not going to be doing that. We're going to be using substitution estimators in this way. So the second point in the second method in NICE's guidelines is propensity score methods. And that is related to the following, that if I have this average treatment effect as follows, it's a fact that I can rewrite it in the following way. I'm not going to derive it here, but it's possible to rewrite this with equalities on every step in terms of this quantity down here. And what we see here is that this is a function of treatment, outcome, and what's called the propensity score. So this is the probability of getting treated given the confounders, W. Now, this is, again, as you can see, it looks fully general, so at least it doesn't suffer from a reading of coefficients. So at present, again, I have the propensity score written in terms of some probability distribution that will be fitted. And if I fit that, I can plug that in. I can plug in the treatment, the outcome, and get the number out. As written down here. So this is good, this is better. So again, let's not worry about coefficients. Let's use things that are substitution estimators, but this is not a home run yet, because what if the fit that I choose for the data is not actually truly reflective of the data generating distribution, and as a result, I make errors and I end up with biased estimate. So this brings me to the third point here, and that is that given that the ground truth is unknown, we need to use statistical and machine learning methodologies that have proven mathematical guarantees that if we follow the steps, we will be able to annihilate or at the very least reduce initial model misspecification bias, but also to maximize detection power because obviously if I make an estimate that has an infinite error bar, I always cover the ground truth, but that's not informative. So it's this interplay between not having misspecification bias, but also being able to maximize power. So the rest of the talk is going to focus on objective 5 here, which is related to closing the statistical gap between what we end up estimating the procedure and the quantity we actually want to estimate perfectly well. So one approach from same parametric estimation theory to do this is target maximum likelihood estimation. And I will not go through the proofs of why this works, but I'll try to show you that the procedure is actually just sort of doing it is not that difficult. And there are well-defined steps of what to do. The first one is that we start with our data generating distribution. So again, for every individual in our population, we have their treatment outcome and confounders. And let's assume for the sake of argument that they are independent and identically distributed. If they are not, there are approaches within TMLE to deal with that, but let's not worry about that for the moment. So now we need to use some method to obtain an estimate of our probability distribution or part of that probability distribution that's denoted by Pn hat. The subscript here refers to the fact that I'm estimating this from my n samples. And we wish this to approximate well the true probability distribution P0. And as I said, usually we don't need the full joint distribution. Usually we just need a part of that, such as the outcome regression or the propensity score. And then once we've fitted this to the best of our ability, we want to evaluate our target quantity of interest, which is this, by plugging in this fitted quantity in and getting out, in this case, the average treatment effect or whatever the question is. It's a Kate or optimal treatment rule or mediation. Now, I will show, I haven't shown, but I will show through some simulations issues with biased estimation or poor coverage if the outcome model is used and is misfitted, or if the propensity score method is used and it's misfitted. So I'll come back to that in a second. But the right approach to use in this kind of scenario is to firstly allow a fair competition between a variety of a diverse library of models. So this is some cross-validation procedure, some refer it as a super learning procedure, where I do the usual CV, the cross-validation, and I have variety of models, such as simple parametric models, all the way to complex machine learning models and neural networks, it doesn't matter what it is. And ideally also fitting methods that I will not have time to go through, such as the highly adaptive lasso, that themselves have mathematical guarantees of coverage later on down the line. Now, this on its own is not going to lead to guarantees of being bias-free. What it does is to at least help that through the setting up of the competition, we end up getting to a good approximation of the two probability distribution. And we can use any algorithm we want. In fact, the recommendation is to use a diverse set, so some simple parametric models as baseline, all the way to something that can be very complicated in order to fit our outcome regression model and propensity score model. But again, I want to emphasize, at this point, we still don't have a guarantee of 95% coverage. So without further knowledge or restrictions on the algorithm generating the estimate, we cannot necessarily ensure or guarantee good behavior with unbiasedness or the smallest possible variance and so on and so forth. And so one approach to remedy this is TMLE, target maximum likelihood estimation, which is a procedure for estimation that has mathematical guarantees that if I were to update my initial fit through this procedure, the difference between the estimated quantity and the true quantity that I want to be estimating follows the central limit theorem in the following way, where this quantity D is the influence function of the estimator. I will not go through that in detail, but essentially you can use it to quantify the variance, the final variance on this estimand using this estimation procedure. Now, how does it do this? Again, this is all done by mathematical theory that we will not go through, but essentially we'll be writing the quantity we're estimating minus truth as a term that is potential residual bias due to model misspecification. So again, we've tried to minimize this bias by having diverse algorithms, but it still is, there's no guarantee that this residual bias is zero. So again, as the sample size grows, if the bias is present, I'm just going to become more and more confident in my bias, and that's not good. The second term is something that's entirely data dependent. So this determines the variance on the estimate. And then there are some finite sample remainder terms that under certain conditions, for example, if the superlearner library is diverse enough, go to zero fast enough. So perhaps we don't need to worry about these ones too much. So pictorially, there are two ways of getting rid of these bias terms. The first is that I can start with my initial estimate that I got out of the superlearner and then add to that this quantity that I can also estimate from data. So this influence function, its shape changes depending on what you're trying to estimate. So for average treatment effect, it has a certain shape. These are sort of well known. For a conditional average treatment effect, is something else. If there is sort of temporal data, if it's two ratios, whatever, depending on the estimand, this changes. But there's a whole zoo of them out there that people know and have derived and are readily usable, essentially. Now, for the estimand of interest, I have the influence function. I can estimate that from data, so I know what my residual bias is, and from that, I can go ahead and reabsorb this into my quantity, the initial estimate. So I'll move the initial estimate by the bias that I've computed, and I essentially annihilate the bias in that way. So this is known as a one-step estimator in the same parametric efficiency theory. So that's one way of doing it. The other way of doing it is TMLE, which is what I'm showing here. So pictorially, what's going to happen is we're going to be starting with some initial estimate in terms of the probability distribution that depends on our data. And this probability distribution is linked to the quantity that we're trying to estimate. That's the average treatment effect. And then somewhere else on this probability space lies my unknown true distribution and true average treatment effect. The mathematical theory behind this basically tells me where I have to move in this infinite dimensional probabilistic space to guarantee that I land somewhere very close to my true distribution, such that if I then quantify my error bars, I don't have issues with bias. Okay? So heuristically speaking, this procedure allows me to set this quantity to zero by moving my initial outcome regression fit in the right direction, nudging it in the right direction in order to make sure that this bias gets killed. Again, for an average treatment effect, it looks something like this. So it ends up being a linear regression in this complex space. And apparently doing it in one step is actually enough. And you see in particular that it depends on this function h, that itself depends on the propensity score. So here's the interesting point. Going back to the NICE guidelines, the current guidelines say either do outcome regression or do propensity score. But methods like one-step estimation and TMLE estimation are known as double robust in the sense that they integrate the best of both. They involve the outcome regression and they involve the propensity score. And as a result of that, as long as we get one of them right, we have the guarantee of being bias-free. And this is where the word double robust comes from, because we have two shots at getting it right. And so as a result, this kind of approach subsumes just doing outcome regression or just doing propensity score regression because it enjoys these double robustness properties and these mathematical guarantees. Okay. So let's do a simulation study to see what happens if we don't have a double robust estimator and if we happen to get the model wrong, which is very likely as the data gets complex. So in this very simple simulation, I have two confounders, W1 and W2. They are correlated with each other. The treatment is Bernoulli distributed in this way. And here we have the propensity score written in the following way. So it's nonlinear in W, and in fact, W1, W2 also have an interaction term in the exponent. The outcome, as far as treatment is concerned, it looks very simple. So it's linear in the treatment and in the confounder, and then there's an interaction term again between the two confounders. And you can remember that we had committed, given our question, to this estimand that was defined model independently. Okay. So let me go ahead and sort of generate data so that I gather statistics. And in this particular case of these plots, I'm repeating the experiment 200 times. So let's say for the sake of argument that for the propensity score, so probability of treatment given confounders, I'm using main term logistic regression. And this is wrong. Because remember that the true generating distribution is something nonlinear and it's highly complex, but what I end up doing is that I just do main terms linear regression. And for the outcome variable, I actually don't misspecify, so I happen to put in a linear model, also take into account the interaction terms. You'll see that in the true case, there's actually no interaction between T and W, and that's fine. So all the model has to do is to make sure it puts this coefficient to 0, but it also captures the other coefficients correctly. So Y is basically well specified, and propensity score is misspecified. So now if I go down the route of the second method, the nicest guideline, which is IPW, propensity score estimation, you see that after I repeat this experiment many times, I'm actually off by a decent amount from the true average treatment effect, which is 1 in this case. So I'm supposed to get 1, but I actually get 1.2 with very high confidence, so I'm overestimating the effect of the drug. On the other hand, because the outcome model is well specified, outcome regression gets it right, happens to be lucky, that's great. And the TMLE approach also gets it right because the theory of this approach guarantees that as long as one of them is right, I'm guaranteed to get it right. And this is what exactly we see here, that the way TMLE is sort of nailing the problem is it's the same way as the outcome model. Now, this problem gets a lot worse, as I said, if we're biased as the sample size grows. So this is done on 2,000 samples. The next one is 20,000 samples. So you see I'm moving away from the ground truth with confidence more and more. And this is exactly the situation we want to be avoiding for the type of sort of policy questions that are relevant for regulatory. So now let me do the opposite way. So the opposite way is a situation where the propensity score method, so the second recommended method in the guidelines, is well specified. So in this case, I have the interaction terms and so on. And in this other simulation, this is fine. But then the outcome model is misspecified. So in this case, just to show you something extreme, I'm taking the outcome model to not even depend on the treatment. So I'm just fitting it to a constant, just taking an average. The second model has the treatment in there, and the third model just assumes some kind of weird sinusoidal thing. So if I fit each of these, I end up with, so for the sine case, this is my initial estimate. So again, I'm pretty off from the true estimate of 1. Then the constant gives me something here. In fact, gives me 0 because it doesn't depend on the treatment. I mean, there's no coefficient to be fitted, so it's 0. And then the other one sort of it also overshoots on the other side. But crucially, when I apply TMLE, what TMLE does is that it shifts the initial estimate in the right direction, and it ends up giving me the right quantity after inference. So again, even though for the TMLE estimate, I've used the outcome model, because the propensity score model was nice and justified, this worked out, and we ended up getting the right estimate. And then you can do this for any kind of complex situation. So they've done more simulations where the situation can be a lot more, like many more variables. It's high dimensional. There are more advanced versions of this TMLE algorithm I mentioned that can deal with high dimensional data as well. And so in this particular case, you might ask, well, in reality, I don't actually just go in with a main terms linear regression. Maybe I'll put in more terms. I try to sort of like put interaction terms between things and so on. I'm going to start with more complex model. So now you could do that. But what happens often in those situations, and we'll see the effects here, that we try to sort of really brute force a larger parametric model in our propensity score fit or our outcome model, It's not getting it wrong, but the error bars are huge because there are like so many parameters that this thing is trying to fit. So I end up losing power. Now, the true outcome model, if I somehow in a God-given way knew what the truth was, this is what it gets. And again, if you see look at the TMLE estimate, its error bar's precision is the same as the true model because it is able to maximize power whilst eliminating model misspecification bias. Whereas if I just made something more complex, yeah, at least I'm not biased, but I may end up with uninformative estimates because of these very large error bars. Okay, so in summary, TMLE is transparent. At least in the case of average treatment effect, to simplify things, it ends up estimating two nuisance functions. So one of them is the outcome regression, the other one is propensity score. Then there's an updating step that's essentially just an MLE. And then based on the influence function, we can do inference in order to extract the error on these quantities. So in these, I'm just going to skip that. So this whole thing is mathematically guaranteed, it's transparent, and what we should do practically is actually not that complicated. Now, the theory is pretty involved, but in practice, this is the recommendation of how to do double robust inference. Okay. So just want to say that target learning has been applied in a whole variety of high impact applications, including randomized control trials and real world evidence. So in the US, some of the notable work that have used this kind of approach was in COVID-19 vaccination efficacy in clinical trials that involved sort of people from academia in a cross-disciplinary collaboration with a US government biostatistics team and industry partners as well. So again, this is not something that is sort of very new. By now it's 20 years old, and the field has really advanced to make all sorts of complicated estimation problems, not just the simple example I went through today. So how have we used this in our group? So there are two main areas of interest in which we have developed TMLE type estimators and applied them. One of them is my field of interest is in genomics. And the challenge in genomics is that typically we're dealing with sort of large scale, high dimensional problem, but also on top of that, very small effect sizes and huge sample sizes. So this is precisely the very bad situation to be in because when we have very large sample sizes, like 500,000 individuals, and the effect size is very small, the slightest bias could be of the same order of effect as the true effect. So I might end up estimating things as 0 when they're not supposed to be. I may end up estimating things as non-zero when they're supposed to be. And then I prioritize the wrong set of DNA variants and genes for further experimental validation. And these experimental validations takes ages, a lot of time, a lot of money. So we really had to make sure that we use approaches that don't suffer from this type of statistical bias, are double robust, and we can really try and get to our small effect sizes in the most precise possible way. So we've ended up adapting some of these estimators for the case of genomics into this software called Targene, which I will not have time to go through. But a lot of this is actually general purpose that we've written down in a scalable manner in this software. That if you're dealing with sort of large scale and speed is of the essence, that this can be used generally. But of course, our interest has been in genomics. The other kind of thing we've applied this kind of estimation strategy to has been in a type of chronic disease called MECFS that I'll just spend 2 minutes on just to tell you sort of why it matters to get these things right, because there are sort of people on the other side and we need to sort of be sure about the statements we're making. So this disease of interest is called ME/CFS, or chronic fatigue syndrome. It affects about 67 million people worldwide, and there are at least 250,000 people in the UK who unfortunately suffer from this disease. 1 in 4 individuals with ME are either housebound or bedbound, and half of the people with ME report deteriorating course of illness. 80% of individuals are female, and the symptoms are highly heterogeneous amongst the individuals. So we try to use the UK Biobank data in terms of individuals' blood counts, metabolites, and proteomics to address the following question. which is related to the deconditioning hypothesis. So this is a pretty old school hypothesis that by now we hope is fairly debunked, but is related to the following statement, that the decline in the physical health of the individual is due to perhaps lack of activity or fear of exercise, and inappropriate behavior in response to symptoms rather than treating ME as a real disease, which actually in a vast majority of the cases starts with an infectious disease that never gets better. So we wanted to address this question in a data-driven manner. And we wanted to sort of make sure that we're able to quantify if the effect of ME on these molecular traits is through reduced activity, or in fact, there's a direct effect of ME on these blood measurements. And so this is a classical example of a mediation analysis. We have to make sure that we correct for certain things like age, sex, and there are sensitivity analysis with BMI and other parameters. But it will not be a fully causal home run because we don't actually know the cause of disease. So we cannot block all the backdoor paths, but at least for a set of observable ones that we're aware of, we can reduce the causal gap massively. But again, we wanted to make sure that at least if we don't have a causal home run, we can kill off the estimation gap. So I'll unfortunately have to skip this, but basically what I wanted to show here is that almost all effects were direct and not indirect through reduced activity. And so there's actually no evidence that it is due to fear of exercise or anything where these changes are in the individual's blood traits. Here we have identified a series of replicated biomarkers that appeared in both males and females separately, where there is a demonstrable large statistical effect, direct effect of ME/CFS on these blood biomarkers. So I'll just skip this and get to the full summary. In summary, we identified 511 blood-based biomarkers whose levels differed significantly between people with ME and those without ME. 116 were independently replicated in disjoint cohorts of males and females, so these were pretty robust. Biomarker differences were not explicable by differences in physical activity. And this provided a strong and replicated evidence for chronic low-level inflammation, insulin resistance, and liver disease. And just want to say that in general, the shift in the traits were modest, so we cannot immediately come up with some kind of a per individual level diagnostic, but we have verified that these differences are in the blood and they are detectable and they are robust. And again, the methodology behind all of this was following the causal roadmap, defining the population, getting to causal identifiability as much as possible, getting to the estimation using these double robust estimation methods that I went through today, just to show a sort of a real world evidence example for this kind of methodology. Okay, thank you. So with that, I'll just stop and take any questions.
Thank you very much. That's terrific. Do we have any questions if you raise your hands or pop something in the chat? I'm not seeing any hands. I don't know whether that's because I'm not seeing it or because it's not there, but okay. So if there's nobody, I just wonder if if you could say a little bit. Oh, sorry, Damien, you've got your hand up. Sorry. Yeah.
Yeah, thank you, James. Thank you, Eva. Really great, interesting presentation. I was wondering when you showed the causal roadmap, these 6 steps, I believe. I was wondering, what do you think about? So we have these estimation steps and almost purely ML, estimation problems, statistical problems. But towards the beginning, we have these problems of defining our problem and the estimates. And I wonder, across all these 6 steps, which are the most, let's say, manual intense, or which require the most kind of human manual thinking, if you like, and if that maybe is more prone to errors because it's more human intense. And I wonder if we can do something about that.
Yeah, I guess the first part is very labor intensive, especially when it comes to real world data. So getting to the right data frame and then matching it to the variables. So first of all, it requires multiple sets of communication with the subject expert. So actually, I should acknowledge my colleagues at NICE because this is a joint collaboration with them and many others who supported in the MECFS paper. But in our work with NICE, because we're actually looking at real world evidence problems, there is a large issue of even if we sit down with the clinicians and we agree these are the confounders, these are the variables, there's obviously a lot of data missingness and how to deal with that and so on. But it's also the issue of like linkage. So we define the problem and then we realize we don't have the data we need because that part of data wasn't in the database. Or then there are these disease codes, and then the encodings are entirely different. So some are doing ICD-10, then there are the GP codes, and then there are like SNOMED codes and so on, and then there are overlaps. So then you're counting people twice if you bring them from. So there is a lot of stuff going on that is a huge bottleneck. Now, once you have a nice clean data frame, even if it has missing data, the next steps are a lot easier to deal with. But that whole like extracting of the appropriate read codes and putting everything together to have like research ready data is very labor intensive.
Yeah. Okay. Thank you very much. So would that mean that essentially this process at the beginning is very much iterative, right? So you
Yes,
talk to
very much
experts,
so.
you
Yeah.
try to formulate a problem, and then go back and again. Okay. Thank you.
Yes, absolutely. Yeah. Thank you.
Okay, thanks. Are there any further questions? If not, I do just would like to hear about Targene a little bit more. As I know you didn't get a
Yes.
chance to go into that.
So that took actually 4 or 5 years of development. But essentially, what we're really interested in is prioritizing DNA variants in our genome that could be nice sort of potential drug targets for experimental validation. And one of the problems of just correlating the variant to the trait is that it misses out on what kind of molecular mechanism we're looking at. So that's one problem. And then the other thing is that just probing the entire genome incurs a huge multiple hypothesis burden, so we don't actually end up finding the appropriate bits. And so one thing we wanted to make sure is that if we have good mechanistic insights of at least where to look, and we're actually after interactions between different DNA variants. We're not really after singular ones because mechanism are typically, oh, this molecule and this molecule need to come together. These effect sizes, because they're higher order, they're statistically very difficult to estimate. So if a single variant, I don't know, has 100% power of detection, the equivalent of effect of the same strength has 50% power. So I immediately sort of dropped. So we really needed to make sure that we sort of are using these kind of double robust estimation strategies to get it with maximal power, but also get it with minimal bias. Because if I prioritize the wrong variant, this is years of experiments down the line that will be a complete waste. I wanted to sort of really ensure not only we have that insight on the mechanism, like where to look, where to increase power, but also make sure we don't get it wrong. Because from an experimentalist, if I prioritize 10 things that are likely valid, is far more appropriate than prioritizing more like 100 things, don't know which one is valid type situation. And so we developed Targene for this purpose for large genetic cohorts. The other challenge I'll say is that when we deal with very large cohorts, depending on how people are sampled, people may be interdependent because there are cousins and second cousins and siblings and so on. So we had to adapt this type of estimator to take that dependence into account, because if you don't, then you may end up underestimating the errors because we pretend they're independent, but they're not. So we have to make sure that that kind of ancestry information or relatedness amongst the individuals is implemented as part of our estimation procedure.
Wonderful. Thank you. Thanks everyone for coming, and yeah, hopefully see you the next one on the 12th of November. And thank you again for a terrific talk, Ava Khamesh. Thank you.
Thank you very much. Bye.